Hello! Welcome to Honors Physics Lesson 3.2, Newton's First Law. He fell. Alright, that's funny. Alright, so this is known as Newton's Law of Inertia, and basically anything at rest is going to stay at rest, anything in motion is going to stay in motion, unless something causes it to change, and that something is called a force. Up too far. There you go. Alright, so some things to remember about inertia. The net force on an object is zero, or if the object's acceleration is zero, or if the velocity is constant, but not necessarily zero. As long as it's constant, then we have no net force. So if one of them is true, they're all true. One of them's false, they're all false. It's an all or nothing type situation. Alright, so a couple other things. As far as it goes, whenever we have a changing velocity, we need a force. So whenever something is accelerating, not necessarily a car, I don't know why I said car, maybe I was looking at cars, I don't know. But anyways, as long as something is accelerating, so speeding up, slowing down, or turning, it needs to have a force on it. We need a force to stop an object, we need a force to change its velocity. But we don't need a force for it to keep doing what it's doing. In other words, keep moving at a constant velocity. No force required for that. Alright, so let's take a look at a bowling ball. Hey, that's a nice bowling ball. Okay, that's a good bowling ball. So when it's sitting on the floor, we don't have any forces acting on it. Sort of. We still have gravity and the normal force. So we'll call that normal force. And clone, and then rotate this way. It's going off the screen. There you go. Acting on it. Okay, so that was delayed. Anyways, so you have normal force and the force of gravity acting on it, and they should be equal, which means that it's not moving up or down, so I can put a little hash mark on there to indicate that they're equal, even if they're not necessarily completely to the millimeter or nanometer equal, but close enough, right? Now, as far as problems go, if these do not pertain, don't even put them in. You don't need to put a free body diagram on every single linear problem. I don't need to know the normal force and the force of gravity. Now, some problems, it might help to have the force of gravity and the force normal. It might. And you might even need to figure out the mass for something. But if it doesn't, if it's just moving left or right, it's giving you a mass or giving you an acceleration, then only include it unless you want to. Otherwise, you're just doing more work, and let's be honest, no one likes to do more work. Alright, so now let's say we have this kid, and he's going to push this ball forward. And in doing so, he is putting a contact force on it. So now I like to draw forward that way, not to be confused with normal force, just the way I picture forward. So we call this force applied, and since it's the kid, I'll just call it force kid. And since it's on something that is frictionless, it's going to move forward, right? So here's our free body diagram. It's moving forward. This means the ball will accelerate, and it will continue to accelerate as long as the kid is pushing it. Once the kid lets go, normal force and force of gravity are the only things that are on it. There's no longer applied force. The thing about an applied force, like Roy pushing something, Sally pushing something, someone pulling something, Mr. H accelerating by throwing a ball, anytime that we have a force that's applied, it's going to be a contact force. So the moment you are no longer in contact, that's the moment that that force no longer is happening. That goes for pretty much everything with the exception, at least in this section, with the exception of the force of gravity. So force of gravity is a non-contact force, kind of like magnets, where you don't need to be in contact in order for that force to happen. But for all of the contact applied forces, friction, normal force, those all need to be in contact. If there was no contact, we don't have that force being applied. Alright, so now the ball hits the pins at the end of the lane, the ball hits the pins, blah, blah, blah. The pins exert a force. It's not a very big force, but it's still a force. There we go. And that would change its acceleration, eventually slowing it down, but its inertia keeps it going because the force gives it a small acceleration, right? So force, if you remember from last section, force equals mass times acceleration. So this has a large mass times a small acceleration. Small force. Alright, so that ends that. Quick, short, to the point. Newton's law of inertia, as well as Galileo, kind of came along the same idea. So sometimes they call it Galileo's law of inertia. But hey, you know, Newton likes to steal people's credit, so yay Newton. Yeah, Newton. Alright, I will talk to you later.